The concentration of a solution is a measure of the amount of solute that is dissolved in a given quantity of solvent. And just a reminder, a solute is the dissolved particle in the solution, and the solvent does the dissolving of the solute. A dilute solution is one that contains a small amount of solute, and a concentrated solution contains a large amount of solute. Molarity, capital M, is the number of moles of solute dissolved in 1 liter of solution. So to calculate molarity, you divide the moles by the volume of the solution. So moles divided by liters. If grams are given to you, you can convert to moles with molar mass. If milliliters are given, just do a simple conversion to liters. So here's an example. What's the molarity of a solution with 0.7 moles of solute and 250 milliliters of solution? Well, we've already got moles, 0.7 moles. We're going to divide by the liters, so we have to convert 250 milliliters to liters by moving the decimal 3 places to the left. And our answer is 2.8 M. Capital M stands for molarity. So 2.8 molar solution. Okay, acid-base theories. There are certain characteristics of acids that we should know. Acids taste sour, they change color with an acid-base indicator, and they can be strong or weak with electrolytes in aqueous solution. So here are some common acids. We have hydrochloric acid, nitric acid, sulfuric acid, phosphoric acid, ethanoic acid, and carbonic acid. Bases taste bitter, feel slippery, change color in an acid-base indicator, and can be strong or weak electrolytes in aqueous solution. An Arrhenius acid are acids that have hydrogen-containing compounds that ionize to yield hydrogen ions, H+, in aqueous solution. Now this often is actually bound as a hydronium ion. So what we see here is that the hydrogen is ionizable. It becomes H+. And in this case, because it's in water, it creates a hydronium ion, which is H2O plus and H+, so it becomes H3O+. Acids that contain one ionizable hydrogen, such as nitric acid, HNO3, are called monoprotic acids. The prot stands for proton. Acids that contain 2 ionizable hydrogens, such as sulfuric acid, H2SO4, are called diprotic acids. Acids that contain 3 ionizable hydrogens, such as phosphoric acid, H3PO4, are called triprotic acids. So the protic is referring directly to the hydrogen. Arrhenius also made a definition for bases, and he said that bases are compounds that ionize to yield hydroxide ions, OH-, in aqueous solution. So just to restate this, hydroxide ions are one of the products of the dissolution of an alkali metal in water. Here are some common bases: potassium hydroxide, sodium hydroxide, calcium hydroxide, and magnesium hydroxide. And you'll notice that the last two, calcium hydroxide and magnesium hydroxide, are not very soluble in water. Now here we have NaOH dissolving in water, and what you see is that it creates sodium ions and hydroxide ions, and the hydroxide ion are why this is considered a base. Now, like we said earlier, calcium hydroxide and magnesium hydroxide are strong bases but have low solubility in water. So what does this really mean? Well, because they're not very soluble, the solution will always be very dilute. Even though it is basic, it's just very, very low in molarity, very diluted. So it's fairly safe to drink like magnesium hydroxide, which is milk of magnesia, which you can find in the store for upset stomach. Now there's trouble with the Arrhenius definition. The definition is not very comprehensive. It doesn't include certain substances that have acidic or basic properties. For example, sodium carbonate and ammonia are basic, but they don't produce a hydroxide. So under the Arrhenius definition, they're not bases, but that's really not true. What we do know is with our Bronsted-Lowry definition, which is a different definition, all Arrhenius acids and bases are Bronsted-Lowry acids and bases. So let's look at the Bronsted-Lowry definition. This theory defines an acid as a hydrogen ion donor and a base as a hydrogen ion acceptor. So here we can see this occurring. So we have ammonia and water, and then the ammonium ion that's produced has accepted a proton, and the water has given away its proton. So we've got hydroxide ion produced. So the ammonia, we know, is the Bronsted-Lowry base because it's a hydrogen ion acceptor. So that's how we know the ammonia is a base with this definition. Now we've got this little back and forth arrow, and what this is telling us is that the reaction can actually go both ways until it reaches an equilibrium, and even at equilibrium the reaction does go in both directions. A conjugate acid is the particle formed when a base gains a hydrogen ion. A conjugate base is the particle that remains when an acid has donated a hydrogen ion. And here we see a base, an acid, and their conjugate acid and base. Notice that a base has a conjugate acid, and an acid has a conjugate base. And this will always be true. We always see them in pairs because we're reacting a base and an acid together. So here we have a hydronium ion, and water is the conjugate base of hydronium. But water could also have a conjugate acid. So a substance that can act as both an acid and a base is said to be amphoteric, and water is amphoteric. In fact, water is the perfect combination of an acid and a base because you can take one hydrogen off of the water molecule and you have H+, and the other part is OH-, so it's made of both an acid and a base.